So thank you, Hardy, to agree to give this TYC highlight seminar. I'm really honored and pleased that you are going to talk to talk today. And okay, you don't really need the introductions. I can also because it would be an hour talk from my side, and I want to spare this. I can say maybe just a couple of things, but it's arbitrary. So what I can say, you did PhD in 1980, then you worked as a postdoc with Walter Kohn, and then become a professor at the University for the, of Würzburg, and then at the Free University of Berlin, then director of the Max Planck Institute in Halle, and now professor of chemistry in the Hebrew University of Jerusalem. The list of honors and awards is enormous. I can cite just a couple of them: the Bernie Alder Seacamp Prize. Hardy is a fellow of the American Physical Society, ERC Advanced Grant, and is a Chevit Lectureship Award. I mean, really, we can go on for hours here. Of course, we all know that Hardy is very famous for having developed the theory for density functional theory of time-dependent systems, and for his work on excitation energies for time-dependent density functional theory, and among other things. And today he will talk about non-adiabatic dynamics. Before I leave the screen to Hardy, I just would like to give a communication. Just I would like to say that if people have questions, please write them in the chat function. And then this is, I mean, a seminar which is organized by the IG1 interest group, which is on methods, and the spokesperson of this group is George Booth. So he will be him who will manage question and answers, and so please put your questions there so that he can select the question and highlight it to Professor Gross. Okay, so that's all from my side. Thanks again, and it's all you for you now.
Yeah, thank you, Lily, for the flattering introduction. I'll try to live up to it. So the talk today is about non-adiabatic dynamics, and I will start with a little motivation. This is a system that is discussed as a possible candidate for photovoltaic applications. It consists of a buckyball here, a porphyrin, and the carotene, and this whole thing is then attached to, let's say, something like a titanium dioxide surface, and so the idea is to create an excitation. So on this porphyrin, it's the chromophore, and then this, let's call it exciton, moves along the backbone here, and it splits on the titanium dioxide surface, creating a photocurrent. And one would like to understand how the details are of this process and maybe be able to speed it up and questions of that kind. So the natural simulation is for such a large system to use real-time DDDFT. And I'm quoting here a calculation that was done by Carlo Andrea Rozzi. He was a postdoc in my group, but not at the time when he did this calculation anymore. So this is his own work. And the simulation here is you keep the nuclei fixed. This is what you tend to do when you come from the electronic structure community. And then you simulate this excitation, and yes, there is visible an excitation. This was the counter here. So the whole process that I showed you was 30 femtoseconds. And yes, there was this excitation here, but the whole point of the simulation to see how the excitron migrates here didn't happen. So complete disaster. So this was a calculation, as I said, for clamped nuclei. And now let's do another calculation where the nuclei are allowed to move. And here you see after a very short time, after the excitation, you see there's density everywhere. And now please have a look in particular at the point of the buckyball here. You see there's a change of color. So it's becoming more and more green. So I should say that what is plotted here is the density difference. So the initial density minus the time evolving density. And you see this becomes more and more green, and there's an oscillation of this kind. So charge moving to the buckyball and away from it on the scale of 75 femtoseconds. And in fact, this was predicted by this calculation with moving nuclei and later confirmed by experiment that there is this oscillation with a periodicity of about 70 femtoseconds. Okay, so that's a bit of a motivation. So even if you talk about electronic excitations, often it's important to move the nuclei as well. So there's hundreds of others motivation. This is just an example that I wanted to show you. So if you want to take the motion of nuclei coupled to electrons seriously, then you have no choice. You have to go back to the Hamiltonian of everything. So the full Hamiltonian of the system of electrons and nuclei, consisting of the nuclear kinetic energy, the nuclear-nuclear Coulomb repulsion, that's here, electronic kinetic energy, electron-electron repulsion, and the electron-nuclear attraction. And with this Hamiltonian, in principle, we have to solve the time-dependent Schroedinger equation if there's an additional external laser field here. So that's, of course, an exceedingly hard task and cannot be done except for very, very small systems. So the way to make progress is usually the following. So first of all, we start from that Hamiltonian that we just had and take the limit of infinite nuclear mass. So infinite nuclear mass means the nuclei don't move. So they don't have a kinetic energy, so the kinetic energy operator is missing here. And as a result, this Hamiltonian, which is known as the Born-Oppenheimer Hamiltonian, depends on the nuclear coordinates only in a parametric sense. So the idea is to then solve this many electron problem at each fixed nuclear configuration, right? And in this way, the eigenfunctions here and the eigenvalues become functions of the nuclear coordinates. So, and here's a cartoon of these so-called Born-Oppenheimer potential energy surfaces. It's a cartoon because this is really a multidimensional dependence. So capital R double underline is the set of all nuclear coordinates, and likewise little r double underline is the set of all electronic coordinates. So that's the first step. And then we use the fact that these Born-Oppenheimer states, remember this is still correlated to many electron states, form a basis in any function that depends on n electronic coordinates. So for a second now, we take the full electron-nuclear wave function and imagine the nuclear coordinate to be fixed, and likewise the time coordinate to be fixed. And then this is just a function of little r, so we can expand it in the complete set of Born-Oppenheimer states. That's exact. And then we imagine we do this at another capital R and another time. And of course, it's still a complete set, so we can expand, but the coefficients will be different. So these coefficients, in other words, will be functions of the nuclear coordinates and of time. So this is an exact, formally exact representation of the complete electron-nuclear wave function. Now, in the next step, we plug this into the time-dependent Schroedinger equation, multiply from the left with the Born-Oppenheimer state, and then we get this coupled set of partial differential equations for these coefficient functions, capital chi sub k. So what appears here is these so-called non-adiabatic couplings of first and second order. So that's weird objects. This is a gradient with respect to the nuclear coordinate, but acting on the subscript, right, on the parametric dependence of the Born-Oppenheimer states. And here a second derivative. So that's the so-called non-adiabatic couplings. And it's these guys that couple the different components chi sub k. Now let's for a sec just assume that these non-adiabatic couplings are small, maybe negligibly small. So let's neglect this term and this term, the second and the third line, and then we are left with something really nice. Just the first line here, that's a time-dependent Schroedinger equation, right? For a nuclear wave packet, chi sub k, and that moves, this wave packet moves in that one Born-Oppenheimer potential energy surface that is plotted here. So we just have one potential energy surface, not many, just one. And the corresponding state, the Born-Oppenheimer state with index k, is this one. We need it at all capital R. And then the corresponding approximation for the full wave function is that nuclear wave packet that goes forth and back here, times the Born-Oppenheimer state that is associated with that surface. This is known as adiabatic approximation. So just remember what we have done here. So we started from an infinite series, and of this infinite series, the Born-Huang expansion, we throw away all terms except one, this one. So that's the adiabatic approximation. Sounds terrible if you think about it. But one thing to remember is that when we calculate vibration spectra, for example, we always make this approximation, right? We take, let's say, the lowest or some higher Born-Oppenheimer surface, just one. And then usually when we make an additional approximation, namely we approximate this by a parabola, so by second order terms only. This is known as harmonic approximation, but these two approximations enter here. So it's kind of pretty much standard. So how come that this is actually a good approximation, having thrown away infinitely many terms? And the answer to that is quite easy. If you think of nuclear vibrations, well, then at least the low-lying vibrations are pretty much down here. So these energy levels are here in the oscillator well. And possible other potential energy surfaces are very far away. So then these non-adiabatic couplings are known to be large in the vicinity of avoided crossings or intersections of Born-Oppenheimer surfaces, but they are large only there. As long as you're here, far away from any other surfaces, you're fine. So this is always a good approximation, except in those cases that is sketched here, when there is another surface very near the minimum, touching or crossing the original surface. Then clearly this other surface plays a role, and then these two approximations, adiabatic and harmonic, just don't work. And then you have to go back to the Born-Huang expansion and calculate the vibrational spectrum from a better representation than the adiabatic representation. So this is more a quantitative failure. I mean, pure adiabatic approximation is not miles away, but it's quantitatively wrong. But there's more dramatic failures of the adiabatic approximation, which I want to show you now. So one class is the famous experiments by Ahmed Zewail. This is the following prototypical case. So we have the system sodium iodide. In red is the lowest Born-Oppenheimer potential surface, and in blue is the next one. And you see here is an avoided crossing. So this lowest surface in the equilibrium region, the electronic wave function has ionic character, while far away, in the asymptotic region, so in the dissociating region, this is neutral fragments. While for the excited surface, it's just the other way around. So here the bonding is not ionic, but rather covalent, and asymptotically it's ionic. Okay, so far so good. So that's the system that we are looking at. And this is a case where other potential energy surfaces are relatively far away. So a good approximation should be to approximate, as you see down here, the full wave function by two terms of the Born-Huang expansion, one that involves the red Born-Oppenheimer state and the other one involving the blue Born-Oppenheimer state. Okay, now the experiment is that you excite from the ground state with a femtosecond laser pulse to this other surface, so you excite the electronic system, but then the nuclear wave packet is not in its ground state anymore, it starts moving, and so if this red surface wasn't there, then you would just go forth and back, just a vibration as I said before. But then, as I mentioned, in this region where these two curves come close to each other, there the non-adiabatic couplings are large, and there then the two contributions get coupled and you create a contribution on the second surface, right? So if you calculate the nuclear density, right, so taking this wave function and integrating over the electronic coordinates and using the orthogonality of the Born-Oppenheimer states, then you end up with these two contributions to the nuclear density, right? So the blue one is this one that goes forth and back here, and then you have a split off part that is associated with the other surface. So this is called the splitting of the nuclear wave packet, right? And in fact, one sees immediately the splitting happens whenever this blue wave packet goes across the non-adiabatic region. Each time, then there's this split off part created. And this can be measured in the pump probe experiment. You measure the outcoming neutral sodium atoms as a function of time delay. And here you can very nicely read off the periodicity of that blue oscillation. And if you start at a different place, then the periodicity will be different. So you see immediately in this way, you can basically map out the upper potential energy surface. And these beautiful experiments were done a long time ago in the 80s and 90s. And in 1999, Ahmed Zewail got the Nobel Prize for this. So everything is perfectly understood within this Born-Huang expansion, in this case involving only two states. But you also see, right, it's essential to have two states, right? If you have only one, right, the whole effect is gone, right? If you only have the blue surface, yeah, you have an oscillation, but what was worth the Nobel Prize here, the splitting off of the nuclear wave packet, that you don't see it. Okay, now let me show yet another case where the adiabatic approximation fails. And that's the calculation of electronic current densities that are associated with nuclear motion. Now, if you think of a nuclear vibration, let's say, but a coherent phonon, let's say, in the time domain, you vibrate, and you ask yourself, what do the electrons do? Well, of course, from this adiabatic picture, you would say the electrons move with the nuclear, right? They go forth and back with the nuclear. So there is a local current density associated with this electronic motion. So let's try to calculate that. So we make the adiabatic approximation, one nuclear wave packet and one Born-Oppenheimer state. And let's calculate the time-dependent electronic density. So it's an n-body density here, but can be one-body density, doesn't matter. So we plug in here the adiabatic approximation and integrate out the nuclear coordinates so that we get the electronic density. And that is fine, very close to the true density, everything perfect. Now we do the same thing for the electronic current density. So that's this operator. So it's the electronic gradient sandwiched between the full wave function in adiabatic approximation. And again, we integrate out the nuclear coordinates here, multiplied with chi squared. And we see here this imaginary part that we need, right, of the Born-Oppenheimer state with the electronic gradient in between, that is 0. Because thinking of the ground state Born-Oppenheimer potential energy surface, right, the eigenstates are real values. Right? That's the eigenfunctions, the lowest energy, normally non-degenerate eigenfunction. That's always real value. Right? So it's wrong, totally wrong, could not be worse. So the current density in adiabatic approximation is 0. So a complete disaster. So now what can we do? So, well, the simple answer is, well, whenever this fails, we have to go back to the Born-Huang expansion. But then Born-Huang is fine if only 2 or very few surfaces are important, like in the Civile experiment, then we can do that. But the big problem is that the Born-Huang expansion for larger molecules or solids even is absolutely not feasible, right? It's just much too hard. To the best of my knowledge, nobody ever tried it for solids. So what can we do? Well, for large systems, think of this triad molecule that I showed you in the very beginning. No way of doing Born-Huang expansion for that. Right? So one thing that one probably would like to, actually one probably has to, treat the nuclear motion somehow in one way or another with classical trajectories. But then immediately we have a problem in this situation when the nuclear wave packet splits. The question is, what is the classical force then when the nuclear wave packet splits? Is it the gradient of the upper or is it the gradient of the lower surface? Right? Fundamental difficulty. And as you all know, if you do things like Ehrenfest dynamics, you get something like an average force, which is not very physical in this kind of situation when you have a split of part. And to cure this, there's this methodology of Tully surface hopping, so that with a stochastic algorithm, you hop between the 2 relevant surfaces with a certain probability. So that is kind of not unplausible because you need the forces of both surfaces, but to the best of my knowledge, this has not been really derived as from higher principles. Now, one of the things that I'm going to show you here in this talk is that this question, what the right classical force is, even in cases when the nuclear wave packet splits, has a unique answer. There's only one correct answer. And I will show you what the answer is. Okay, so the way we do that is with the method that we have termed exact factorization. One can view this as exactification of the adiabatic approximation. So it has the same feature that it is one electronic state times one nuclear wave function. So it's not a sum, like in the Born-Huang expansion, but there's differences. You see, for example, here in the adiabatic approximation, this is a Born-Oppenheimer eigenfunction. Here, this is something else, right? This is even time dependent. Okay, so this is now the end of the long introduction, and I will show you how one can make plausible that this is actually an exact representation of the full electron-nuclear wave function. And then I will briefly, very briefly, talk about the concept of an exact geometric phase that follows from this exact factorization. And then I will show you that this, in fact, leads to the concept of an exact classical force on the nuclei. And then, after these more conceptual points, I will discuss two very different kind of applications. One is a way of treating this problem of electronic currents associated with nuclear motion, and the other is a mixed quantum classical algorithm that is able to describe non-adiabatic dynamics, but without surface hopping and without decoherence corrections. Okay, so before I start, I want to thank all the many people that have contributed to what I'm going to show. So the whole thing started with Ali Abedi when he was a PhD student in my group. So he created the formal framework for the time-dependent case. Nikita Skidopoulos created the same framework for the time-independent case. And then other people here, Federica, who is also listening today, was working on this mixed quantum classical algorithm, also Seung-Kyu Min, Ivano Tavernelli, and Vasil as well. Nipa Maitra was also involved in other aspects of the mixed quantum classical formulation, and she was also contributing to the very first fundamental paper. And Axel was working on dealing with the electronic current densities and the application to dichroism, vibrational dichroism, that was really driven by Rodolphe Villenier. And Ryan Request, who is still in my group now, he is working on applications for solids. Okay, so here's the first theorem. As I already indicated, this whole formalism comes in two varieties. One is the static version and one is the time-dependent version. So I will start with the static version. So there we have the stationary Schroedinger equation. And the theorem says that this full electron-nuclear wave function can be written as a single product of one electronic wave function, which is similar to Born-Oppenheimer. It depends kind of parametrically on the nuclear coordinates and is a many electron wave function, times a nuclear wave packet. And the feature that one requires for this electronic part is that it is normalized to 1 for each fixed nuclear configuration. Okay, so that's basically the theorem. One can also show that these factors are essentially unique up to within an R-dependent, capital R-dependent gauge transformation. Now, when one sees that first, from the audience of my talks, I typically get two reactions. One reaction is that this is absolutely impossible to be true, because thinking of the Born-Huang expansion, we need infinitely many terms of this kind. So how can this be that one such term does the whole job? So there one has to say, well, the infinite expansion, this is one way of representing it, but that's Born-Oppenheimer states. This guy here is not a Born-Oppenheimer state. This is something much more general. So then the other reaction is, well, actually, it's totally trivial. Well, if one thinks of, well, doing something trivial for this nuclear wave function, like setting it like a plane wave or so, or something similar, then you see that essentially this guy becomes identical to 1, to this one on the left-hand side. So that's too simple. That you cannot do. That's important to realize why this cannot be. And this is because this normalization condition. Right? This means that you are normalized to 1 for each fixed nuclear configuration, while this guy here, being a proper wave function, is normalized to 1 by integrating the absolute square over all coordinates, over the electronic and the nuclear coordinates. So if this guy is essentially the same as this, then you cannot satisfy this normalization condition. Okay, now the deeper reason why this is actually true is essentially a theorem of stochasticity. Right there we know that a joint probability can always be written as the product of a marginal probability times a conditional probability. And that's exactly what we have here. Think of the absolute square of the left-hand side. That's the joint probability of finding the electrons at little r and the nuclei at capital R. And this joint probability can be written as a conditional probability. That's the absolute square of this guy. And that's why this guy is normalized to 1, right? The probability of finding the electrons at little r, if we know for sure that the nuclei are at capital R, right? That's a conditional probability density. And that's a marginal probability density. So absolute square of this is the probability of finding the nuclei at capital R. So for the absolute values of this equation, it's totally obvious that this has to be true. And then one just needs to show that the phases don't cause you troubles, so to say. So that's the proof. So now comes the more tricky part. So the first part, the first theorem is kind of obvious if you think of this probabilistic theorem. Now, knowing that such a single product can be the true wave function, we just plug it in the variational principle and optimize the 2 factors. And after some 20 pages of algebra, we end up with these 2 equations for the 2 factors. So let's first have a look at the nuclear factor. So that's a nice Schroedinger equation. We have, like in Born-Oppenheimer, here a potential energy surface, which is the eigenvalue of the electronic equation. And in addition, we have here a vector potential. And we call this the exact potential energy surface and the exact vector potential or exact Berry connection, because it has a very peculiar structure. Right? It is a gradient with respect to a nuclear coordinate acting on the subscript here, on the parametric dependence on the nuclear coordinates, and we integrate out the electronic degrees of freedom. So it's a function of nuclear coordinates, and it has the structure of a so-called Berry connection. So this appears here. So that's what we get for the nuclear equation. So the electronic equation is a bit more complicated. First of all, we get the Born-Oppenheimer Hamiltonian here, and we get 2 additional terms. These 2 are proportional to 1 of the nuclear mass. So loosely speaking, once we take the infinite nuclear mass limit, then these terms go away. Actually, that limit is a bit more tricky, but roughly speaking, that's true. And then we're back to Born-Oppenheimer, the infinite nuclear mass limit, as we should. Now, these terms are complicated. First of all, the nuclear wave function appears here, this grad chi over chi term, with the chi that comes from the other equation. So if one thinks of solving these equations, one has to do this kind of self-consistently, both equations. And then there's this vector potential appearing here as well. So this makes it actually a nonlinear equation in phi. And in addition, there's this gradients with respect to nuclear coordinates acting on the parametric dependence. So it's a very complicated operator. Okay, but that's what you get. All right, now there's these exact potential energy surfaces. That's the eigenvalue here. Let's have a look how they look like. And so for this, we first need, it's useful to have a model system which we really can solve exactly. And there a very nice one is the one by Shin and Metyu. It consists of two heavy nuclei, very heavy nuclei that are clamped so they don't move. And then in addition to that, one has a movable nucleus that is allowed to move here along the axis, and one electron that is also allowed to move along this axis. And in addition, one has certain effective interactions, things like screened Coulomb interactions. And so this is a simple enough system that one can solve exactly, and one can solve it in Born-Oppenheimer, and that's what you see here. That's the Born-Oppenheimer potential energy surfaces, the three lowest ones. And now let's compare with the exact surfaces. And let me go forth and back a little bit here. You see that they are kind of like diabatic surfaces, so they cross. Right? Okay, now what can we say about this Berry connection? So this is the definition again. So now let's use the fact that the electronic factor is the full wave function divided by the nuclear factor, and let's rewrite the nuclear factor in absolute value and the phase. And then after 2 or 3 lines or so, we end up with the vector potential being identical to this expression here, gradient of the phase. And if you take a close look here, this is the exact nuclear current density, right? So this nuclear current density operator, but calculated from the full electron-nuclear wave function. So that's the proper nuclear current density that you get from the full wave function by tracing out the electronic degrees of freedom. And that's the nuclear density. So this is roughly a velocity field, one could say. Okay, so that's what we get, right? So this vector potential has nothing to do with electrodynamics, right? It's essentially the nuclear velocity. So another way of writing this equation, we just solve it for the current density. Now, in this form, it looks very familiar. We have learned in quantum mechanics 1 that if we have a Schrödinger equation with a scalar potential and a vector potential, then the current density associated with this Schrödinger equation is given by this expression. So if you gave me this Schrödinger equation, which is the nuclear Schrödinger equation that I just showed you, we would calculate the current from this. But remember, this is not where we derived it from. We came from here and plugged in here the exact current density that follows from integrating out the electronic degrees of freedom from the full wave function. So what this tells you is that this equation, the nuclear equation, if I just take it and calculate the current from it, it gives you the true nuclear current density. And it also, that's what I said before, it gives you also the nuclear density. So when I say density, I almost mean n-body density and n-body current density. So let's take a step back. This is something very unusual. Normally, if we have a system that consists of 2 subsystems, like here, we have electrons and nuclei, to calculate the property of one subsystem, one needs a density matrix. Not here, not for this observable. We can get the true current density of the nuclei from this single nuclear Schrödinger equation. That's unusual. I'm not claiming that this nuclear Schrödinger equation gives all nuclear observables, but at least the current density and the density, so n-body current, n-body density, comes out right. And this, by the way, with respect to later, this is primarily what you actually want to reproduce if you involve trajectories, right? So you want the density and the current density. That's what you want to reproduce. Okay, now this is just a side remark. I'm not going to dwell on that. This Berry connection, this exact Berry connection also defines what one could call an exact geometric phase. And there's whole books written about this molecular Berry phase within Born-Oppenheimer. So it raises the question, are those the same, right? Or is there deviations between the Born-Oppenheimer Berry phase and the exact one? And we investigated this question for, again, a model system that we can solve exactly. It's the Shin-Matthew model, but now in 2D. So this nucleus and this nucleus is again fixed. And then the electron and the other nucleus, they are allowed to move around in the plane, right? So this is then 4 degrees of freedom, xy for this nucleus, xy for this electron. So this is still simple enough to solve it exactly numerically. Here are the Born-Oppenheimer surfaces for this problem. And here's a conical intersection. And the proper Born-Oppenheimer Berry phase of pi is associated with it. And if we then, for that same system, we calculate the exact geometric phase that follows from the exact vector potential, turns out it's 0. So for this particular system, one could rightfully say that this whole Berry phase business is just an artifact. Right? In the real world, which is the exact vector potential, right, it disappears. And so for a while, we believed that this is always true, but then we actually discovered another system, another model that is depicted here. So it's again a triangular situation, and the relevant nuclear mode is a pseudo-rotation where these 3 nuclei go around their equilibrium position kind of in a concerted way. And for this mode, turns out also the exact Berry phase is non-zero. So there are actually 2 cases of Born-Oppenheimer Berry phase. The ones that kind of are an artifact that don't survive in the exact treatment, and then there's the other case where they do survive. So this is just a side remark. Some people, we are now in the age of topology, may find this interesting. So now let's continue with a time-dependent case. So there again, we have 2 theorems that are very similar to the static case. So now we have the full time-dependent Schrödinger equation. And the statement is that again, the full time-dependent electron-nuclear wave function can also be written by a single product. And now this electronic factor not only depends parametrically on the nuclear coordinate, but also on time. And this has to be normalized to 1 for any fixed nuclear configuration and any fixed time. And the physical meaning is, of course, once again, that of a conditional probability amplitude. Now, the equations of motion are reminiscent to the ones that we got in the static case. So first of all, for the nuclei, we get a nice time-dependent Schrödinger equation. Again, we have what we would call an exact potential energy surface and an exact vector potential. Exact in the sense that the product of these 2 wave functions gives the true result. And then let's have a look at the electronic equation. So here again, this nuclear wave function appears. So one has to propagate in time these two equations in parallel. Again, this vector potential appears, which makes this equation nonlinear. We have the Born-Oppenheimer term and these two terms that are proportional to 1 over the nuclear mass. So in principle, that's a small parameter here, which is nice, and we will explore that later. So this is what you get. So let me summarize these properties of these two equations. So first of all, as I said, the electronic equation is now a nonlinear equation in phi because the vector potential contains the phi. Then one should emphasize that these operators here, a nuclear momentum operator acting here on the subscript, right? This is not really, strictly speaking, an operator in the electronic Hilbert space. It's something weird. But if we pretend it's an operator and use the Born-Oppenheimer basis to represent the action of this operator in a matrix, then we realize that this operator corresponds to a matrix that is actually non-Hermitian. Right? So this non-hermiticity will become important. It's a feature that just comes out here from the variational principle. In spite of this non-hermiticity, the time propagation conserves the norm. And in the static case, the eigenvalues are real. One can prove that. So that's an interesting aspect, right? It's non-Hermitian, but still the time propagation conserves the norm. But we will see that later, is responsible for describing decoherence correctly. Okay, and the electronic equation also depends on the nuclear wave function. Nuclear equation of motion is much more simple. So it's a time-dependent Schroedinger equation with a scalar potential and a vector potential, where both of these potentials are n-body interactions. So this is kind of expected. If you think of Born-Oppenheimer, the Born-Oppenheimer surface is also an n-body scalar potential. So this is what you get. Now there's a third theorem, and this is the same story that I showed you before for the static case, namely that the nuclear Schroedinger equation that I showed you not only yields the true nuclear n-body density, but also the true nuclear n-body current density. That true one that one would obtain from taking the full electron-nuclear wave function and integrating out the electronic degrees of freedom. So this Schroedinger equation, the nuclear Schroedinger equation, gives us the true density and current density. And this means if we want to reproduce in some sort of classical trajectory setup the true nuclear density and the true nuclear current density, we have to use this Schroedinger equation. There's no choice. And then once we have the potentials in that Schroedinger equation, we know that the gradient of this time-dependent potential energy surface is the correct classical force, even when the nuclear wave packet splits. This and only this is the correct classical force. Unique up to within a gauge transformation. So like always, we can shuffle parts of the scalar potential to the vector potential. That's always possible. Okay, now how do these exact time-dependent potential energy surfaces look like? So for this, we did a model calculation that is supposed to mimic the Zeeweil experiment. So we start with a nuclear wave packet in blue here. This is a calculation, I should say, for H2 plus in 1D, time propagated. So that's again an exact calculation if you wish. And so we start in the upper Born-Oppenheimer surface as initial state. So initially, the true surface is parallel to the upper Born-Huang surface. So what is plotted here, this is the upper Born-Huang surface. This is just as a guide for the eye. And in green here, this is the lower, the ground state Born-Huang surface. And now we go forward, a series of snapshots here. And in red, what is plotted in red, that's the exact time-dependent potential energy surface. I should emphasize, so these kind of vertical lines or spikes, this is just numerics, comes from the fact that the nuclear wave packet at these places is already something like 10 to the minus 20 or so. So there's no physical significance to this. I'm just totally honest here. I just show you what comes out of the computer directly. But this is just to be ignored. So it's only this middle part that is to be looked at, where the nuclear density is sizable. So we propagate here, and then something funny is beginning to develop here. And we propagate further, and now you see what you expect, namely that the nuclear wave packet splits. Right? That's exactly the Tseweyl experiment. Now you see at the place where the overlap is minimal, there's a step developing here. Right? And one can actually show that analytically that when the overlap between these two split-off parts of the nuclear wave packet becomes exponentially small, then this step becomes infinitely steep. So now let's look at this again. A step, right? This very much smells like surface hopping. Like if it becomes totally vertical, it would be a jump of the classical force from that surface to that surface, right? So it looks like surface hopping in a way, but it's not. Right? So what I'm showing you here is just the time-dependent Schroedinger equation plotted in a somewhat unusual fashion. It's nothing but the time-dependent Schroedinger equation. Okay, so now an important point. So on the exact level, these two equations of motion, they're perfectly equivalent to the full time-dependent Schroedinger equation. So it doesn't really make much sense to solve them for an exactly solvable model. One can do it. It's actually numerically harder than the original time-dependent Schroedinger equation. So there's not much point. But the crucial advantage of this is that the nuclei and the electrons satisfy separate equations. And this is useful as a starting point to make approximations. Right? And I will show you two very different classes of approximations in the remaining minutes of my talk. First type of approximation you see here. This is the electronic Schroedinger equation. And as I said before, these weird terms that come in addition to the Born-Oppenheimer part, they have a small prefactors, 1 over the nuclear mass. So this invites you kind of to do perturbation theory. And this is exactly what we do. And we then calculate the electronic currents that are associated with slow nuclear motion, like a vibration, in perturbation theory, where we treat these red terms here as perturbation. So first a model study, just to fix ideas. So this is a model, very simple model for a 2D, an electron in 2D, and a nucleus that moves in 1D. And there's another very heavy nucleus that is clamped at the origin. And all these particles interact with soft Coulomb potentials, so that's what's written here. And the propagation is started. So what is plotted here is the lowest 20 or so Born-Oppenheimer surfaces for this problem. And we start the propagation here in one of the two wells. And what you expect is that then this is like a double well problem, that you will get something like tunneling oscillations here. And I'm going to show you now what the picture is after half of the nuclear wave packet has tunneled through. So this is kind of at a quarter of the tunneling oscillation period. Right? So this is where it started originally, and now half of it has gone to the other side. This is a plot of the nuclear current density. So far away from this interesting region, there's no current. But then there's current going through this barrier in the middle, right? That's the tunneling. After all, these nuclei go through as a function of time. And what you see here now is the electronic density. So as expected, if there's nuclear density here and nuclear density here, the electrons move kind of, or the one electron moves kind of with the nuclei. So there's a probability, large probability here at this maximum, and another large probability here. And this is the plot of the electronic current density. What you see here is what you get from the exact solution. And if you do this first order perturbation theory treatment that I indicated before, compare with the exact one, this is nearly perfect. Right? So the thing that I want to emphasize is in adiabatic approximation, this lower plot here for the electronic current density is strictly zero. This is what I demonstrated before. So, and now in first order perturbation theory, this comes out very nicely. So this reproduction of electronic current densities associated with nuclear motion is actually a very hard one. And the reason is that if you want to do this with the Born-Huang expansion, you need very many terms. So it's numerically it's a super difficult problem. While here, if you treat these weird terms here in perturbation theory, just first order perturbation theory, then it comes out nicely. And there's actually a very real world application to this, and this is vibrational circular dichroism. So dichroism is the absorption difference between left-handed and right-handed circularly polarized light. Expression is this for the dichroic response. And what is the relevant quantity that we need to calculate is the so-called rotational strength. And what enters there is this electric dipole and this orbital magnetic dipole, one could call it. So this is really the electronic and nuclear current operator. So this for a rotational current, this for a linear current. And that's the important point. So there's an electronic contribution and a nuclear contribution in both cases, right? And in the adiabatic approximation, you get a contribution from this nuclear part, but you don't get a contribution from the electronic part. And that's the problem. So there's a really important aspect, right? This experimental quantity, rotational vibrational dichroism, doesn't come out right because a sizable part of the response is just zero. Now, if we do this with the exact factorization, right, we have these two contributions, electronic and nuclear, and so electronic, if we plug in here the Born-Oppenheimer state, which is the zero order term, these are zero, because it's current. And then in first order perturbation theory, you get a contribution and you can calculate this dichroic response that I showed you before. And we did this for the deuterated oxyrane molecule that you see here, which is known to have a strong dichroic vibrational response. And here's then this rotational strength calculated with our approach, this perturbative approach. and with a different approach, which is much more complicated, essentially involves kind of a Born-Huang expansion, but then makes further going approximations. So it's a quantity that's very difficult to calculate, as you can imagine. And as you see here, well, not exactly the same, but so for this object, the dichroic response, it's even very difficult to reproduce the sign, right? And at least the sign comes out correctly everywhere here. So this is a good indication. So we have a very efficient way here to calculate this quantity. Now for the final minute or so, I will show you a completely different way of exploring this exact factorization in constructing an algorithm that could be called a mixed quantum classical algorithm, where nuclear motion is treated with classical trajectories, while the electrons are treated quantum mechanically. So here are the two equations. So the idea is to represent this nuclear wave packet in terms of classical nuclear trajectories. And as I emphasized before, no need for Tully surface hopping, no need for decoherence corrections. All we do is we use here the correct, as I would emphasize, classical force, which is the gradient of this object, the time-dependent potential energy surface. Now we still need to do something with this first equation. This is horrendously complicated. It's still a correlated many electron problem. And this we density functionalize. There's different ways of doing that. I won't have the time to discuss that in detail, but this is what we do. And then if we first apply this again to our favorite model, the Shin-Meityu model, you see that you can describe very nicely the splitting of the nuclear wave packet here with the classical trajectories. So this is this non-adiabatic effect of splitting of the wave packet. And an aspect that maybe is even more exciting is that we, if we plot a measure of decoherence, it's essentially an off-diagonal element of the electronic density matrix in Born-Oppenheimer basis. And if we do the full quantum calculation, that's plotted in green here, right? It should go to 0, which it does. That's decoherence. The off-diagonal elements of the density matrix go to 0. And if you do surface hopping, or Ehrenfest for sure, but also surface hopping, you don't have decoherence. This is a well-known problem of surface hopping. While if you use the right forces without any further effort, you get decoherence. It's not perfect, so it doesn't really go to 0 here, so there's room for improvement. But okay, this is what you get. And now this algorithm that I mentioned, so this classical trajectories for the nuclei and time-dependent density functional theory for the electronic degrees of freedom is sufficiently simply implemented that one can actually treat real-world systems. And here's an example for that. It's the oxyrain molecule, and that has essentially, when you expose it to a laser field, two mechanisms of ring opening. One is the carbon-carbon stretch, and the other is that the oxygen here goes to one of the carbons. And for this system, beginning with a wave packet that we imagine has been produced by a femtosecond laser pulse, we are able to predict that the ring opening mechanism by oxygen motion is much larger than the carbon-carbon stretch. And like in the model calculation, we find that this measure of decoherence plotting it and comparing with the fewest switches surface hopping, where you don't have decoherence, comes out very nicely without any decoherence corrections from our algorithm. If you add decoherence corrections to this fewest switches surface hopping, then you get this curve. So you can get this with other patches as well. But our formalism just gives it for free. So I should also mention this algorithm, which was developed by Federica and Sung Kyu Min and Ivano Tavernelli. This is implemented in the CPMD code, and so everybody is free to use it. And this is pretty much what I wanted to say. So the take-home messages are that this formalism of exact factorization is on one hand useful to settle conceptual issues like finding out what the correct classical, unique classical force is on the nuclei, even when the nuclear wave packet splits. And it defines something like an exact geometric phase without the need of doing a Born-Huang approximation. And it is also useful to develop practical algorithms. So one was the mixed quantum classical algorithm that does not need surface hopping nor decoherence corrections. And a totally different way of using these equations is to treat the non-adiabatic terms in the electronic Schroedinger equation by perturbation theory. And this allows you to calculate vibrational dichroism and electronic current densities more in a very reliable way. Okay, that's it. Thank you for your attention.
Thanks. Can you hear me, Hardy?
Yes, yes.
Hi, yes. So I mean, I will sort of lead this Q&A. I'm the spokesperson of the methods interest group, and I of course just first of all want to sincerely thank you on behalf of everyone in the audience who's listening and the whole of the TYC for a very inspiring and thought-provoking talk on some of the fundamentals of molecular quantum mechanics that many of us take for granted. And we're also, very sad that you can't come to London in person, but I hope you'll, once everything calms down, you'll still consider it an open invitation to come to London and see all of us in person.
Thank you. I'll take you up on that.
Good. We look forward to it. We've slightly run over time, but this is a highlight seminar, so I certainly hope people will stay for a few questions. And if you have any questions, please shout in any way that I will be able to see, maybe through asking questions in the chat functionality or raising hands or anything else that you feel is appropriate. But as the sort of chair's prerogative, if I could start off by asking a quick question first while other people have a chance to write them in the chat function. I'd just ask, there was beautiful insight from all of this exact factorization and the work that was done on the model systems. And I guess my question is more from a practical perspective now. You presented later on the prospect of doing this perturbative expansion and that the algorithm's now implemented in CPMD. What does it actually, what's the actual overhead over a normal DFT calculation of including this, these nuclear dynamics in this way, and what is the prospect of the sort of systems that will be able to treat? Is there some sort of self-consistency that is still required between the two parts of the wave function in order to do this? And yeah, I guess what is the prospects for numerics in realistic systems going forward?
Yes, so basically what the algorithm ultimately boils down to is you have a term that is identical to Ehrenfest dynamics, and you have an additional term that involves quantities that you, if you do surface hopping, would want to calculate anyways. So surface hopping, you calculate these probabilities from the non-adiabatic coupling matrix elements. So these things enter in the other equation as well. So that's from that point of view, it's not much harder. Now, how many trajectories you need to kind of resolve the nuclear wave function, that is another question. And this is, there's not so much experience yet on this. So some people explore this and similar algorithms like Seung-Kyu Min, who was postdoc and who partly developed this, who is going further with this now in Korea. So he made some progress, but it's not exceedingly more difficult, I would say.
Okay, fantastic. So I mean, I know that your, you know, some of your other work has been doing superconducting density functional theory. I mean, is there any prospect on the horizon of really having a kind of exact factorization approach to kind of anharmonic phonons with the electronic method?
Putting all complications together.
Something for the future then.
Yes. Well, what we are working on is in fact real-time dynamics of superconductors. Right? I have one PhD student here who works on this. And so it touches the exact factorization because these non-adiabatic terms that I showed you come in there as well. It's a slightly different way they look like because ultimately everything is formulated in terms of phonons and kind of time-dependent quantum electrons. But yes, so in fact, we are working on this.
Fantastic. All right, we have some questions in the chat functionality as well.
So one of the goals there, I should mention this, is to describe this currently rather hot topic of laser-induced phase transitions. So there's these experiments that you hit a magnetic system, which is kind of a parent material of the ITC superconductors with a laser pulse, and then at least for a short period, you have an excited state of the superconductor, right? So it's a magnetic to superconducting phase transition in the time domain, so triggered by a laser pulse. So this kind of questions is what we are after.
Excellent. Okay, that sounds like very interesting. So there are a few questions in the chat functionality that I might just read out. So one, for instance, is asking about temperature effects. So this is all temperature equals zero theory. Is there an extension for finite temperature, and how might that change things?
Yes, so that's a tricky question, because it touches this question what actually temperature should be or should do when you have a strongly driven system. And this is, even from the most fundamental point of view, not really a well understood topic. So what I can tell you is you can do linear response. And that's straightforward to do from equilibrium, right? If you start from equilibrium, you can kind of propagate each single state with this factorization and go from there. It's not really much explored yet.
But this is zero temperature linear response?
No, this is finite temperature.
Finite temperature.
Okay.
Okay.
So that's the point, right? So you start with equilibrium and you perturb from there with a weak external perturbation, and then you propagate in time, right? Because it's a time-dependent perturbation, and you start from all these eigenstates that are occupied with a Boltzmann distribution initially, right? And then you propagate from there. And for each state that you propagate, you can do this propagation that I showed you. It's kind of clear that you can do it. Whether you can deduce from that something useful, like, let's say, propagation of factorized form of the density matrix itself, that's another question. And Federica has worked on this. I don't know what the current status of this is, so I may defer the question to her. So the question, can you actually do something similar, some factorization of this kind for the statistical matrix, for the density matrix? That's a slightly different question. So okay. I don't know where we stand on this currently.
Okay. A question from Jochen. Does the mixed quantum classical algorithm preserve total energy when summed over all interacting trajectories?
It should. Now, there are little tricks in the algorithm that may ultimately not make you conserve this. That is a tricky question. So in principle, what I showed you, right, this decomposition of the nuclear wave function in terms of trajectories, in principle, this could be made exact if you included in your equations the Born potential. But in our algorithm, for the time being, we have actually neglected that. So there are little tricky points that in the present manifestation of the algorithm might affect that. So I'm not sure if you now ask me for that particular calculation, let's say for the oxy-rain, whether we actually have tested that. So Federica, you are here. Do you remember that?
Yeah, hi.
Hi.
So yes, the point is that we do not have the form. So if you just sum the kinetic energy of the nuclei plus the potential energy of the nuclei over all the trajectories, this is not strictly conserved. It's because in principle you should also include an extra term coming from the quantum momentum, because what is conserved is the quantum energy, which has so to say the nuclear kinetic energy term coming from the gradient of the phase of the nuclear wave function, but plus you have an extra term that accounts for the spreading of the nuclear wave function in time, over time. So you should in principle take into account also this effect to conserve the energy. So just summing the nuclear kinetic energy and the potential energy is not conserved because this is not the quantum kinetic energy. So this is what standard quantum classical methods try to conserve, because they are somehow empirically determined, empirically derived. If you come from the quantum derivation, you have this extra term that you have to consider also with the trajectories, and these are
okay. That makes sense. So there's a related follow-up question to that, which is asking to which extent the mixed quantum classical algorithm accounts for different types of nuclear quantum effects other than the electronic decoherence, for instance, tunneling.
Yeah, so tunneling this is already partly answered with what I just said, is not included in the current algorithm. So if you think of something like a barrier just within one potential energy surface, and a nuclear wave packet comes along and tunnels through, then in this classical trajectory decomposition of the wave packet, it's essential to have the Born potential, which we neglect. So we have the non-adiabatic transition, so splitting of the wave packet, but we do not have tunneling in one single surface. That is not included in the present algorithm. Other effects, we have one paper that discusses to which extent you can, with this formalism, represent interferences. So if you have a split-off part of the wave function and then it comes together again, and then you have interferences. So this, from the point of view of the factorization, this you actually can reproduce. Now, to which extent then the mixed quantum classical part is able to do that, we haven't really investigated. But there I'm kind of optimistic that this should be possible. Okay,
great. So there are some questions from Nikitas. So the first one concerns this idea of avoided versus true intersections between potential energy surfaces. So the question asks, so it's about, conical intersections versus avoided crossings. So if an avoided crossing has a gap of something minuscule, 10 to the minus 200 EV, how can you tell whether it's a conical intersection or avoided crossing? And Berry would suggest that you go around the intersection and you see whether you acquire a phase to see whether it's a true intersection. So in the example you found where the exact Berry phase is 0, would it be a touching point between the two surfaces rather than a true intersection?
Okay, so so this part of this question really goes to the traditional Born-Oppenheimer Berry phase situation. Is there a difference between a true intersection and so a true conical intersection and a tiny little 10 to the minus 20 gap avoided crossing? And of course, physically, there cannot be a difference, right? But mathematically, there is. So for the true intersection, if there is a Berry phase associated, even if the gap is 10 to the minus 20 electron volts, if you go around, you get 0 if it's an avoided crossing, and you get pi if it's a true intersection. For the exact Berry phase, it doesn't matter. And that's one thing that I like about it, right? So it's not, it's much more physical, right? It's just intuitively, there cannot be a difference, right, between a gap of 10 to the minus 20 and no gap. And indeed, for the exact phase, that's the case. Okay. I should also say, so the exact phase is usually not quantized. So it's what one could distinguish between a geometric phase and a topological phase. So the Born-Oppenheimer phase is usually a topological phase. So it's either pi or 0, while the exact phase can be any number in between, right? And there you can see already, it doesn't matter if there's a 10 to the minus 20 gap.
Okay, so another question. In treating nuclei classically on the exact surface, there's somewhat of a dichotomy, right? To find the exact potential energy surface, we need the nuclear wave function. If the nuclei are treated classically, where do we get the nuclear wave function from?
Yes, so how do we do this in practice? there's different ways of doing it, but basically we decorate this is common practice to decorate the trajectories with Gaussians and then kind of superimpose those Gaussians, and this is then taken as approximation for the nuclear wave function. Right? But it sounds kind of trivial, but in principle this is exact. Right? So this decomposing a wave function in terms of trajectories is, in practice, of course, always approximate, but as you make your trajectories denser and denser, this is an, in principle, exact way of solving quantum mechanics. Right? So there's nothing wrong with this. Right? But of course, in practice, it depends on how you do it. If you kind of freeze these Gaussians, or if you allow the width to change, and this kind of details that matter in practice.
Okay, just a couple more questions, if you're happy to take them.
Absolutely.
In the perturbation theory, how many terms do you keep in the infinite sum? I'm not sure exactly which part that's referring to, but presumably the perturbative expansion of these coupling terms. So
this first algorithm that I showed you for the dichroism,
yeah,
that is just first order perturbation theory.
Okay.
Just the first term, when we treat these terms here as perturbation, first order.
Great. And a question from Duncan: any thoughts towards the prospect/practicality of reaction dynamics with an embedded exact factorization approach?
Yeah, one should do it, I think. Yes.
Okay. And a final one regarding the Berry phase and the geometric phase. You said that for some systems, the geometric phase is 0 when the Berry phase is non-zero, and for some systems, both are non-zero. What's the simplest system where one gets non-zero geometric phase?
So the generic situation where you get a non-zero exact phase is when you have a nuclear current whose curl doesn't vanish. So remember, you can see this immediately from the equation that I showed you in the beginning, that this one here, that the vector potential, right, whose loop integral gives you the Berry phase, is essentially the velocity field, right? So it's the current density. If this velocity field has a non-vanishing curl, right? So if you go around somewhere with your nuclear degrees of freedom, so rotational degrees of freedom typically, right? Then if you go around, then the curl of this current density is not 0, and then the curl of that vector potential is also not 0, and then you cannot gauge it away, and then you have a Berry phase. So that's the prototypical situation, and the examples that we have found are of that kind.
Okay, I think that makes sense. Well, I think the questions have somewhat dried up, but we've gone over half an hour over time, so I think the number of questions really reflects the interest and enthusiasm everyone had for this talk. So on behalf of the TYC and everyone, I'd like to thank you again for giving an excellent talk and making yourself available for us.
Thank you so much.
All right.
Thank you for your interest.
No worries. Okay, thank you. And thank you all for being here. And yes, we will hope to see you all again soon at another TYC event.
Thank you.
Thank you.